Hello, Tuskegee University students. This is Dr. Gerald Griffin, and today I will be discussing some major themes related to our second week in Biology 315, General Neurobiology. In this first video for this week, I will highlight major concepts related to Chapter 2 in your Purves et al. Textbook. Just to review, last week we discussed the function and structure of the neuron. Now we will focus on the electrical properties of the neuron. Neurons, if they are alive, will always have a voltage reading. You may remember from chemistry or physics courses that voltage is the product of I, current, times R, resistance. What are the major sources of current and resistance in the neuron? Well, the major contributor to current in the neuron is the flow of ions inside and outside of the neuron. Ions such as sodium or potassium can flow in or out of the neuron via channels. This does not require any energy. Also, pumps that require energy will pump ions against their chemical and concentration gradients, allowing for there to always be some difference in chemical and ionic charges across the membrane. This difference in chemical composition and ion concentrations gives rise to the neuron's voltage. The major contributor to resistance for the neuron is this phospholipid bilayer. All those actions will give rise to the resting membrane potential. That is to say that even if the neuron is not activated, it hasn't been stimulated by some experimental or natural source, the neuron will always have a potential. It will always have a voltage. So whenever I say the word potential, you should always think voltage of the neuron. Another potential that is commonly seen in activated neurons is the action potential. Action potentials are described most often as all or none. That means that either you will have an action potential or you will not have an action potential. It is like the basic light switch that most of us are used to. Either you can click on and the light is on, or you click off and there is darkness. There is no dimmer switch for action potentials in the neuron. You will not change the amplitude, you will not stretch it out to be wider or shorter. You either will have action potentials or you will not have them. Let's discuss more in detail the shape and the events that arise to give the action potential. You can see here, as denoted as the RMP, which stands for resting membrane potential, neurons are highly negative at rest, and most sit around negative 90, negative 70, if you will. This is just an illustration, but indeed most neurons are anywhere between negative 60 and negative 70 millivolts at their resting membrane potential. If there is some stimulation, the neuron will become more positive, and we call this process of removing negativity and becoming more positive depolarization. So we are removing the polarity, we are removing negativity and becoming more positive. This depolarization occurs due to the opening of voltage-gated sodium channels, allowing for sodium to come into the neuron, giving an increase in positive current and becoming more positive, more depolarized. The neuron is going to try to reach the equilibrium potential discussed in Chapter 2, which is about positive 50 for sodium. So the neuron is going to try to reach the equilibrium potential for sodium. It doesn't quite reach it, and you should understand why that happens. around positive 35 millivolts, these voltage-gated sodium channels become inactive and voltage-gated potassium channels open. Well, what's going to happen then? Well, potassium is going to flow out of the cell, causing a huge rush of positive current to leave the neuron, hyperpolarizing the cell. And now we get to become more negative, if you will. We are going back to that polarity in that negative state. In fact, we become so hyperpolarized, we go beyond the initial resting membrane potential, and we have what many term an undershoot. You need to understand why there is an undershoot. Why, during the action potential, in this falling phase, does the neuron become more negative than it was initially? And then after some time, the neuron will return back to the original resting membrane potential. Now you may have noticed that I crossed out a word in this figure, and that word was closure, that the sodium voltage-gated channels here close. That is not correct. These voltage-gated sodium channels inactivate. And so just like a pipe or a drain in a sink that is always open, these sodium channels at this point are still open. Ions could enter the top part of the channel or the extracellular portion of the channel. However, intracellularly, there is a plug that comes in. And so just like your drain, when it gets clogged, water can't flow properly and can't go past that clog point. Well, just like that, these clogged up sodium channels will not allow sodium ions to flow through completely. And therefore, they cannot enter the cell and they cannot further depolarize the cell. I know that was probably a lot, but I really want to just highlight the fact that neurons have voltage and the reasons for why they have voltage, and explain some of the mechanisms, the major mechanisms for the action potential that's seen in stimulated neurons. That is the first major goal for week 2, related to chapter 2 in neuroscience by Purves et al. The major goal for this week is that you should understand how the actions of ions and their channels contribute to the resting membrane potential and the action potential. If you can describe all those steps and understand how the channels are working, you should feel very confident in your mastery of this material. If not, again, I'm available by office hours, phone, email, Twitter, and of course, you can come to the problem-solving sessions in person. That's it for this first video, and remember that there is a second video related to week 2 that will describe major concepts in chapter 4 of your textbook. Thanks and have a great day.